Okay, I want to start with just a little intro to Gauss's law and just kind of talk about the relationship for a moment before we dive into this problem. So, if I could just get your attention up at here, where I have Gauss's law written out. One of the things I want you to notice about it, and this is the form I have it in, it's slightly different from your book, but it's pretty much the same. Epsilon naught times the flux is equal to the enclosed charge. So I want you to notice that Gauss's law, as it's written, does not have an E field anywhere in it, right? It just is relating the electric flux to the enclosed charge. That's important. So like take that in for a second. And then the electric flux is the piece where we get the electric field related. So electric flux then here is the integral E dot dA. And if you haven't spent time on flux yet, I would say stop this video right now and go back and make sure that the concept of flux is clear to you. That's important before you can actually work on this application. So we're using Gauss's law as we're solving this problem, but I just wanted to kind of introduce this. My general approach in a Gaussian problem when I use Gauss's law is I tend to focus on first the left side of the equation, and that is defining the flux, and then the right side of the equation, and that is defining the enclosed charge. And then once I have those two quantities defined, I then relate them using Gauss's law. One of the reasons I model that is that students can tend to get into circular logic, and you might find yourself doing that, doing some circular reasoning with Gauss's law. And this is a way to avoid that circular reasoning issue coming up, is if you know that for each problem that you pursue, you need to define the flux and you need to define the enclosed charge. You relate those two things to one another in order to solve for E. That's the general approach for Gauss. So I want us to start with this situation here. Let's turn our attention to the application. Um, you're looking at a cross section of a spherical object. These are concentric charged objects. They're two objects actually. Let me grab my highlighter here. In the center, you have an insulating sphere of radius A. So kind of take that in. I always tell students, imagine that's like a styrofoam ball. It's solid. Okay. Radius A there. We're told that that has a uniform charge density rho. Rho is, of course, charge per unit volume. You should know the notation for linear charge, surface charge, and then volumetric charge as well. So we know it has a uniform charge density rho, and we know that it has some total charge positive big Q. So we know that about the styrofoam ball in the middle. And then concentric with that is a conducting shell. So imagine when you see conductors in this class, imagine them just as being something metal. That's easier. And when you see an insulator, imagine it as being some kind of foam or something, piece of styrofoam, if that's helpful. So on the outside here, the shell that's concentric with the ball in the middle is conducting. That's important, right? It's metal, and it also has zero net charge. Okay, so that's what we're starting with. This is, I know it seems kind of complex, but it's actually a fairly simple case for us to start with. And notice that what we're asked to determine here is we're asked to determine the electric field in all regions. So all regions, what's that going to mean? That'll mean inside the styrofoam ball, right, from 0 to A, between the styrofoam ball and the shell, between A and B, inside the shell, between B and C, and then from the outside of the shell to infinity, the rest of the universe. Okay, so we can handle that. We're going to do it one region at a time. So we're going to start here with region 1, and that is the region, I'll just go out radially. So I'm going to go ahead and start here at the region inside the styrofoam ball. So when we use Gauss's law, it involves placing a Gaussian surface. And hopefully it makes some sense to you that the surface that you need to use is a closed surface. So I guess I'm just going to change colors for my Gaussian stuff here. I'll use green for Gauss. And that means that I'm going to place a Gaussian surface inside the styrofoam ball. Now, I'm just drawing a cross section of that surface, but the surface itself that I'm using is a sphere. I'm going to say it has some radius r. So my Gaussian surface is a closed surface. It's a sphere, and I'm placing it inside that styrofoam ball. I get to do that because a Gaussian surface is an imaginary surface, right? So I can do whatever I want with it. It has to be well defined. You have to know its shape, and then, of course, it has to be a closed surface, and we're going to integrate over or consider every single part of that surface. So I'm actually going to use a sphere as my Gaussian surface for every part of this problem. All right, so now I'm focused on the Gaussian surface that I've placed inside of this styrofoam ball here. And the first thing that I want to calculate is the flux. So remember, I was going to do them in order. So I'll label that here for this first time. We want to calculate flux. Okay, so the flux, let's write our equation. We have a closed surface integral here, E dotted in with dA. Now dA, of course, is an area vector, and remember that it is always directed outward. So dA is always directed outward. Outward normal is how it's defined in this case. And so now I need to think about what is the relationship between my E field here and dA. dA is the easy one to draw in. I get to define that. That's totally up to me because I've defined the Gaussian surface. So dA is just simply the outward normal on whatever piece of surface that I'm looking at. So the trickier part is then to figure out spatially what's the direction of E. I care about the direction of E and dA because look at this, I'm pulling a scalar product here. This is not just a multiplication, okay? These are two vectors, and because it's a scalar product, that means I care about the angle in between them or how they're spatially related to each other. So dA is what I would describe as radially outward everywhere on that in the ball. And the cool thing is that E is also going to be radially outward everywhere. So E and dA are parallel. And I want you to just pause for a minute and think about why, when I say E is radially outward everywhere, right? Why that would be. There's a little bit to that. One is the case that when we're using Gauss's law, we only consider the charge that's inside. You can think about it that way. So you can think about the charged ball that we're enclosing with our Gaussian surface. That's just kind of like a big point charge. So it's going, and then we know it's positively charged. So it's going to act just kind of like a big point charge. And when I'm outside it, it's going to have radially outward electric field. The other thing I can notice is that I'm going to use a different color here to, let's see. This part that's outside my Gaussian surface, this part that I'm kind of shading in right now, that's going to be, think about it, that's going to be a shell, right? That's going to be a charged shell of material. And think about, is that going to have any kind of E field contribution to the space inside it on the Gaussian surface? And there are a lot of different ways to see that, but that's something that's known as shell theorem. And it works in gravitation or by looking at electric field. Either way, it is the same, that it's not going to exert any electric, or not going to create any electric field inside it. So there's no electric field contribution from that outside part that I'm not enclosing. So what that means here is that I have a really nice simple relationship between E and dA. So I'm going to say here where E is parallel to dA everywhere. Right? So since they're parallel, that means that we know that we have like we multiply by cosine 0, which is basically what that means physically, is that all of the electric field is going to permeate my Gaussian surface. all of the electric field gets through. So all of the electric field in this case contributes to flux. That's what we're saying. So to calculate my flux then, it turns out to be pretty simple. My electric field is constant and the same everywhere. And really all I'm doing here is I'm integrating all my dAs. And that, remember what that is that's the area of your Gaussian surface, right? So that's going to be just E times the surface area of my Gaussian sphere, which is 4 pi r squared. Okay, so that's my flux. My flux is simply E times 4 pi r squared. So I have the left side of my equation done. Now I need to figure out the right side. So I'm going to say here, now the next step here is to calculate the enclosed charge. So we calculated phi. Now we need to calculate the enclosed charge. So my charge enclosed here, I'm not enclosing the whole ball, so I can't just say Q, right? But I know the charge density. So the enclosed charge is just going to be the charge density, that's a given in this problem, multiplied by the volume I'm enclosing. And I'm enclosing 4/3 pi r cubed. That's my enclosed volume in my Gaussian surface. So when you're applying Gauss's law, something you have to like really stay focused on is that you're finding when you're focused on flux or focused on Q enclosed, either one of those, it's the Gaussian surface that you're looking at, the Gaussian surface that you're analyzing. Okay, so I've figured out, I've gotten my flux, I've gotten my Q enclosed. What I'm going to do now, and I'm running out of space a little bit, so I'm going to do it over here, is I'm going to relate those two in Gauss's law. So Gauss's law tells me that epsilon naught times flux equals my enclosed charge, and that's exactly how I'm going to use it. Epsilon naught times my flux, and my flux in this case is E 4 pi r squared, right, is equal to my enclosed charge. And my enclosed charge in this case is rho times 4/3 pi r cubed. Now, all I have to do here is solve for E. And what I get is rho r over 3 epsilon naught. And that is the electric field inside the styrofoam ball. So this is a magnitude only here. There's no hat on that. I'm just finding magnitude right now. I know it's radially outward, but I'm just going to be focused on magnitude. This corresponds to R less than A, or applies to R less than A only. And that's good. This is kind of an interesting outcome. If you look at it, R's in the numerator, that's kind of unexpected. Normally we think about a field dropping off, and that's true in space, in free space, but we're not in free space when we're inside the styrofoam ball, right? We're like inside charged material. So the electric field has this really interesting behavior where it's 0 at the center of the ball, yeah, when R equals 0, and then increases, right? You see that linearly, kind of weird, as you go out radially. And this is again a simple case where the charge density is uniform, but that's kind of an interesting outcome for this one. Okay, so we have found our electric field for this first region, the region inside the styrofoam ball. So let's go on and look at another region. We're going to move outward now, and we're going to look at the region between, we looked at 0 to A, so we're now going to look at the region between A and B, and I'm going to put my Gaussian surface. Every time I want you to do this, draw in where you're putting your Gaussian surface. So I'm going to put, my Gaussian surface is still a sphere, and I'm putting it, I always put it in, pretend that's a circle, I always put it into the region that I'm analyzing. So that's where I do it. I plunk it right here. And this is some radius r. It can vary. It has to vary, right? Because it has to apply to everything in between between A and B. Okay. So again, it's a sphere. I place it there, and then I do my same calculations here. And this is going to kind of get repetitive, but that's okay. Right now, if it gets boring, then that's good. That means Yeah, it's making some sense, hopefully. So let's calculate flux again, and I'm going to remind us that flux is E dotted in with dA here. So now I need to pause and I need to think about, I know what my dA looks like, right? Because I have defined that surface. So dA is always outward normal to the surface. That's the dA direction. The magnitude is a tiny little piece of area. Okay, cool. So that's always the first thing that you can draw in. And now for E, I need to think about what is the direction of the E field in this region. Well, if that inner styrofoam ball is a big positive charge, right? Which I know it is, right? We were told that it's a big like positive Q in there. And this outer shell is neutral, then I know very well that my electric field is going to look like this in this region, right? My electric field is going to be going from the styrofoam ball everywhere in this region. I'll just draw it in over here. From the positively from the styrofoam ball to the shell in there, radially outward, basically, again. So I know I've got that. That tells me that E and dA are parallel again. So what I end up with here, I'll write this out again here, where E is parallel to dA, right? So what I end up with here is my E field. And again, I'm going to look at adding up all my dAs as I go over my whole surface. And that ends up being E times 4 pi r squared. Again, it's a sphere, kind of boring. And then I find my Q enclosed. And this time my Q enclosed is really simple. And again, remember, this is, what am I enclosing by my Gaussian surface? My Gaussian surface is just enclosing that styrofoam ball. That's it. So my Q enclosed is just that big Q. That's it. So when I apply Gauss now, Gauss's law tells me that epsilon naught times my flux is equal to the enclosed charge. So let me sub into that. Epsilon naught times flux, and flux here for me is again E times 4 pi r squared, is equal to my enclosed charge, which this time is Q. So if I solve for E, I get something that possibly is familiar to you, which is Q over 4 pi epsilon naught r squared. That's otherwise known as KQ over r squared. And that's just the expression for E field due to a point charge, which is how the styrofoam ball behaves when you're outside it. So because it's a sphere, that's why. So because it's a sphere and we're talking about 3 space, right? As sphere has symmetry in all dimensions, then when you're outside that sphere, it's going to act just as if it were a point charge located at its geometric center. Same thing. A planet would be the same way if you're looking at gravitational field. When you're outside the planet field looks the same as if the entire mass of that planet were concentrated at the geometric center, or center of mass of the planet, I should say. Okay, so this is our result here that applies to our, R being between A and B. Okay, so it acts like a point charge there. Let's move along to the next region. So next region here is between B and C. So you know exactly what I'm going to do here. I'm going to put my Gaussian surface now inside this region. This shell has some thickness. It's non-zero thickness, right? So I can totally put my Gaussian surface in there. And then my Gaussian surface will have some radius r. R is between B and C. There you go. So this is kind of cool. Remember that this shell out here is a conductor. Okay? This shell out here is a conductor. So there's something that we haven't gotten to yet, but I still want to talk through it right now. And that is that this conductor, an isolated conductor like this with a static conductor, the electric field inside conducting material like this is always equal to 0. So I'm going to remind us right now that this charge is plus Q. The shell out here has no net charge. So what I can just say here is that inside conducting material, this is true for static charge. Again, we'll get to the theorem about this, but I just want to introduce you to it now. So inside conducting material, I can say here E is equal to 0, and I'm going to say right now by something called CICT. That's the charged isolated conductor theorem. I'm going to say that again. That's the charged isolated conductor theorem. So that was, hopefully, if you went through the reading and videos that I assigned, you went through that one. It's one that I'm going to expect you to use. So just please try to kind of take that in. Charged isolated conductor theorem. And it has to be isolated. It's different from like when you have a wire. Once we get to looking at circuits, then you have a non-zero E field inside a conductor. That's why you have current through the wire. So that's not an isolated conductor. Okay, so I know that inside this thing that the E field is equal to 0, and I know that by theorem. So that's all I need to do for this part. So once you kind of get to know the theorem, the nice thing about a theorem like this is you can just kind of pull that theorem out and say, hey, that's a conductor. And inside that conductor, inside the conducting material, by this theorem, and this conductor isn't connected to anything else, so it is isolated. It's influenced by other stuff, but it's not connected to anything else, not touching anything else. I can say that the E field is 0. So then I'm done with that region and I can move on. The last region that we're dealing with here is the region that's outside C. So it's now outside like the whole enchilada out here, right? And again, I'm using a sphere as my Gaussian surface. Gaussian surface is a sphere of radius r. I want to remind us that this little ball in the middle has a charge Q and that there's no net charge in the shell. So that's the charge that I'm dealing with right there. And then let's go through our steps again, finding the flux here. Now this is kind of an interesting one. Just remind us of this integral here, E dot dA. So when we're calculating flux, what do we care about? We care about E and we care about dA. Once again, dA is easy. I know it's outward normal, right? So dA is radially outward because I've chosen a sphere as my surface. Outward normal is well defined as radially outward. So the question then might be like, well, what is the electric field out there? And you'll get a better feeling for this as time goes on and you do a little bit more of these, but the electric field out there is radially outward. There are a couple different ways you can think about that right now. One way you might think about that is that the ball in the middle is positively charged. The shell has no net charge. So the entire E field in the area around it is only influenced by the styrofoam ball. And let's kind of go with that way of thinking about it right now. And then we'll bring in some other physical influences in a little bit. So let's just say that, okay, the only charge that's inside of this Gaussian surface is a positive charge. So our best guess at this E field is that it is radially outward as well. So I would say that out here, my E field matches once again with dA. So E is parallel to dA again. So I'm going to say again that E is parallel to dA. Maybe you're seeing why this is an introductory case where these things kind of keep turning out this simple way. So to calculate my flux again, E multiplied by just summing all my dAs, which is again going to give me 4 pi r squared. It's still a sphere, so the area is still the same. And all of my E contributes to flux, so I don't have to worry about losing any components of anything there. My enclosed charge, and remember this is the charge that's enclosed by my Gaussian surface, that's still just big Q because the shell, I'm enclosing the shell now, but the shell doesn't have any net charge. So out here, you see that we're going to get the same result as last time, right? So when we apply Gauss, what we're going to get is epsilon naught times E 4 pi r squared equal Q. That's going to give me E is equal to Q over 4 pi epsilon naught r squared, which is the same as the point charge. This turns out this is KQ over r squared, right? Same as our point charge equation. Okay, so then the question would be like, oh my gosh, so once you're outside the shell, it also acts like a point charge. So that's kind of interesting. It acts like a point charge in the region between A and B. Between B and C goes to 0, right? Because you're in a conductor. And then as soon as you get out of C and go to infinity, then it acts like a point charge again. KQ over r squared. Okay, so we're going to look at the why of this for just a moment here, because I have one more question on here, and that is, let's determine the induced charge on the conducting shell. So induced charge might be a concept that you're just getting to know, but I want us to think about it. It's going to help pull some of the behavior together here. So in order to answer this question, I'm going to use Gauss for this again, and I'm going to place my Gaussian surface on the inner material here of this conducting shell again. And the Gaussian surface is a sphere again of radius r. And I'm also going to remind us that this sphere in here has a positive charge Q. All right, so to run through this, to find the induced charge, what I can say here, I have to use some logic. So the first thing I can say is that I know that the electric field where I've put my Gaussian surface is equal to 0, and that's by the charged isolated conductor theorem. And then what I can say is, if my E field equals 0, then flux equals 0. And that's by the definition of flux. So remember that flux is the integral of E dot dA. So if you crank that integral and set E to 0, it's going to take the whole thing to 0, right? Because when you dot 0 in with dA. So that means that if I know that my E is 0 in there, I know my flux is 0. Okay. Notice that that logic doesn't work the other way around. I just want to throw that out there. If someone tells you that the flux is 0, that doesn't mean the E field's 0. I'll let you think about that. The next thing I can say then is, if flux is 0, then what does that mean? That means Q enclosed equals 0. And that is by Gauss's law, because those are the two quantities that Gauss relates, right? So if flux is 0, which I've just shown it is, then I can conclude that the enclosed charge is 0 as well, because that's what Gauss's law says. Remember, Gauss's law says that epsilon naught times the flux equals the enclosed charge. Gauss's law is one of Maxwell's equations, so we can feel pretty good about it, I think. All right, so our conclusion here, like a big conclusion for us then, is that, guess what? Our enclosed charge is equal to 0. This is going to help us answer the question about where the charge is sitting. So if our enclosed charge is equal to 0, let's think about that. Look at the Gaussian surface. Okay, you know you have a positive big Q in the styrofoam ball. You've known that the whole time. So in order for the enclosed charge to be 0, which it must be, right? That, like, the logic is tight there. It must be. So in order for that to be true, that must mean that I have to change my pen. That must mean that we have a charge of negative big Q sitting on the inside of the shell. So I'm going to take that in. You have negative big Q sitting on the inside of the shell. That must be true, because when I add up all the charge in my Gaussian surface, it has to sum to 0. It has to. So I have to do this. This must be true so that I can say that the Q enclosed is going to be equal to the negative Q plus the positive Q, right? Which will equal 0. So check. Great. My Q enclosed has to be 0. All right, this has another implication though. Now, if I say that, like, oh my gosh, this must mean that there's a negative Q on the inside of the shell. Well, this shell still has a negative, or sorry, it still has a 0 net charge. We didn't change that. We can't change that. It still has a 0 net charge. So if there's negative Q on the inside of the shell and the shell has a 0 net charge, what charge must sit on the outside? It must have positive Q on the outside. When we sum up all the charge on the shell, it still must line up with what we were told initially about the shell, and that is it has a 0 net charge. So now we know the induced charge on the shell. The shell we have negative Q on the inside surface of the shell. It has to sit on the surface. We don't have charge inside of conducting material by theorem. It has to sit on the surface. It can be all over the surface. It's just inside the material, E is 0. And then we have positive Q on the outside surface of the shell. And this is what we call our induced charge. And you can kind of see why we call it that. It's just basically a charge separation that occurs. The shell isn't all of a sudden charged, right? It's still net 0. But because charge separation happens, one of the things that happens that's interesting is it acts like a charged object. So now think about the outside of the shell. Now you realize why it's acting, why the field out there is radially outward, right? This shell has little positive charges all over the outside of it. And it has little negative charges all over the inside of it. How does that happen? Well, the electrons see the big positively charged ball in the middle and they are like, I want to go to that. And so the electrons all hang out on the middle, or sorry, all hang out on the inner surface of the shell, leaving behind positive charge. So that helps explain. I like that because it helps explain why it is that we would have this electric field, radially outward electric field everywhere outside the shell, and why it would act like a point charge. Okay, so hopefully that made some sense. You will probably have to go back and look at certain parts of that, but this was meant to be your introduction to Gauss's law. There's more to come.